Hi everyone. So this is the review session for the first long exam of Triple E3. So in this session, I'll be going through the questions from last semester's exam. And so let's get straight into it. So the first question is, the following resistance RA is equal to 10 ohms, RB is equal to 15 ohms, and RC is equal to 25 ohms are connected in delta. And we're looking to compute for its Y-connected equivalent resistance. So for this, the very first thing that I would do is to visualize the circuit. So we do know that these resistors are connected in delta, and with that, that means it would look somewhat like this. So we could actually plot in these resistances in wherever you want to put it. So for example, what I do is I'll put R sub A is equal to 10 ohms at the top, and then R sub B is equal to 15 ohms here, and then RC is equal to 25 ohms. And then we actually have to convert this into the Y connected equivalent resistance. So that would mean that it would look somewhat like this. And then let's just say the points, these particular points would be 1, 2, and 3. So this would be 1, this would be 2, this would be 3. And this will be R1, R2, and then this one will be R3. And then next, now that we have it visualized, we then plug in the values. So if we want to find the Y-connected equivalent resistance, it's just the division between the product of the adjacent R delta connections of the resistors all over the sum of all of these delta connected resistors. So first, when we solve for R1, that would be equal to RA times RB all over the sum of all of these resistors. So RA plus RB plus RC. And if we were to just plot these out, that would be 10 times 15 all over 10 plus 15 plus 25. And then if we were to just multiply and add, that will be 150 over 50, and that's equal to 3 ohms. So R sub 1 is equal to 3 ohms. And then for R2, that would be RA times RC all over RA plus RB plus RC. And for that, RA times RC is just 10 times 25. Then we already found the sum of all of the resistors connected in delta, and that's 50. So that's 250 over 50, which is equal to 5 ohms. Then for the R3, that would be RB times RC, which is all over RA plus RB plus RC. And that's going to be equal to 15 times 25 all over 50. And then that will be equal to 7.5 ohms. So yeah, that's basically it for number 1. So now let's move on to questions 2 to 4. And so for number 2, that's to identify the number of nodes, loops, and meshes. And then the third question is between nodal and mesh analysis, which method will result in a less number of unknowns? So for number 2, let's first look into the number of nodes. So the nodes depend on how many branches are the ones that connect the circuit elements. So looking into this, that would first be this one. And then next would be this part of the circuit. And then this one as well, since it connects this resistor and this resistor. And then the fourth one would be the one at the very bottom, since it connects all of these circuit elements. So that would mean that we actually have 4 nodes. And the next, we will now look into the number of loops. So the number of loops depends on how many closed loops, or basically how many closed paths do we have. And this means this is irregardless of interlap or anything like that. So that would mean that our number of loops would be this one first. So that's 1, 2, 3, and then we have one here, 4, 5, and then we have a very, very big loop, which is this one. So that's 6. So we have 6 loops. Then for the mesh, it's similar to a loop, except there is no overlapping. So that would mean that would just be this one, 1, 2, and 3. So we have 3 meshes. So now that we've answered number 2, the next would be to compare between nodal and mesh analysis variables. So just a note for nodal, the number of variables is equal to the number of nodes minus 1. So that would be, since we already know the number of nodes, which is 4, that will be 4 minus 1, which is just 3. So we have 3 variables for nodal. And then for mesh, that's the number of meshes, which we also saw a while ago as 3. So that means that for both, they both have the same number, so you can actually just put either for this. And yeah, that's for all. Actually, for number 4, it was a bonus question in our exam last sem, so we won't be covering that in this one. And then now, let's move on to the second part of the questions, which is the nodal and mesh analysis. So we are told to use the circuit below for the next questions. So for A, which is nodal analysis, we are tasked to redraw the current and clearly label the nodes, voltages, and currents for each node. And second is to set up the nodal equations and also to solve for the nodal voltages. And then for B, which is the mesh analysis, we will also have to redraw the circuit, clearly indicating the mesh currents and polarities, and also to set up the mesh equations and solve these mesh currents. So first, in terms of redrawing, what we could actually do is, redraw the circuit first, and take note that for resistors, since they consume energy, their signs would be from positive to negative. And then for the currents, you can actually just assume the direction based on the signs of our resistors. So first, uh given that we've already redrawn the circuit, let's now first label the nodes. So for that, that would be first, this would be our first node, which I'll label as A, our second node here, which is B, and then this would be our third, C, and then our fourth, which is D here. And then this would be actually our fifth, E, but we could also take note that this is our ground already, since it's at the very bottom of our circuit. And now that we have that, next, let's look into now labeling our voltages. So, well, for the voltages, that's just gonna be, we've already found the nodes, so we can just put a V on it. So since these are gonna be our variables, so VA, VB, VC, and VT, and then our E is the ground, so we don't really need to put any voltage for that. And then our next would be to label the currents. So for the currents, what I would do is to first identify the signs in our resistors. So for that you could just do this arbitrarily. So let's just assume let's say for this 200 ohm resistor, it will be from negative to positive, and then for this 80 ohms, it will be positive, negative. Usually what I do here is to arbitrarily put the signs is to base it from, let's say we already know that there's a 750 MA here, and it's going upwards. So based from my knowledge of resistors that are going positive to negative, then I'll just assume that, this current will go this way. Although that's just an assumption, and you can actually have a different answer for that. And then here for the 40 ohms, that will be positive to negative, so that, the current will end up going like this. And then last for the 50 ohms, it will be positive to negative as well here. And with that, we could actually identify our currents. So the currents that we'll need to take note here is the currents in our resistors. So knowing that currents go from positive to negative in resistors, that means for 200 ohms, the current will be going to the left. So that's I 200. And then for the 80 ohms, it's going to the right, I 80. And then for 40 ohms, it's going downwards, so I 40. And then for the 50 ohms, it's going downwards as well. So that's I 50. So yeah, that's it for the first question. And then next is to set up the nodal equations. So when we set up the nodal equations, we should first determine all the known values. And so usually for nodal analysis, the known values are usually on the nodes in which there's a voltage source that's connected to the ground. And that would be this one only. So we do know here that VA is equal to 50 volts. So with that, we already know that we don't need to solve for VA. And now we have VB, VC, and VT as our unknown voltages. So with that, we can make KCL equations for them. So first, for the KCL equation at node B, we do know that the summation of the currents going to this node is equal to the summation of currents going out of this node. And so for VB, based on our directions of the current, we do know the ones going in would be 750 MA and 50 MA, and then the ones going out would be I80 and I200. So if we were to just write that down, just like this, so what we'd end up having is for the in, that would be 750 times 10 raised to negative 3, since it's MA, then plus 500 times 10 raised to negative 3, and then equal that to I200 plus I80. And then if we were to just add these two values, that would be equal to 1.25, and that's going to be equal to I200 plus I80, but we could actually convert these now into V over R, since we do know that V is equal to IR, just to make it a bit easier for us and just so that we could immediately solve for the voltages. So for I200, which is this one over here, it will be VB minus VA, since VA is the negative one. So VB minus VA, which is gonna be VB minus 50, since we do know VA is 50. Then divide that by the resistor, which is 200. Then for I80, that would be VB minus VC over 80. So that would be VB minus VC over 80. And that will be our first equation. And the next equation we could actually make is the supernode at CD. So a supernode is basically when a voltage source is not connected to the ground and is in between two nodes. So that would be this one over here, and it's connected at C and at D. So for that, we could actually treat this whole thing as one node. And so doing the similar process of summation of current in is equal to summation of current out. The ones going in this whole super node would be I80, and then the ones going out is 500 MA, I50, and I40. So if we were to just write that down right now, that would be I80 is equal to I40 plus 500 times 10 raised to negative 3, then plus I50. And then similar to what we did for the KCL equation at node B, we could actually convert these all into our voltage variables. So for I80, it's going to be a similar equation to a while ago. So that's just VB minus VC over 80 is equal to, for I40, that will be VC minus the ground, but since for the ground, we just, we can ignore that so that it will just be VC over 40. So that will be VC over 40 plus 500 times 10 raised to negative 3 plus for I-50, it's gonna be VD minus the ground. So that's just VD over 50. So that's VD over 50. And that's gonna be our second equation. And so since we have two equations already, but we have three variables, we have to determine our third equation. And since we have a supernode, that means our third equation will come from that. So that will just be 10 volts is equal to VC, since that's the positive side, minus VD, which is the negative side. So that's just 10 is equal to VC minus VD. And that will be our third equation. So if we were to just put them all together, what we could actually do is first line up all of the similar variables. So our variables should be VB, VC, and VD. So what we could do there is just separate example for VB minus 50 over 20. That's just going to be equal to VB over 200 minus 50 over 200. So what ends up happening is we isolate the constant. So that will be equal to VB over 200, which is 1 over 200 times VB. Then let's check out the other variables. So there's also a VB here. So that will be equal to VB over 80 minus VC over 80. So we could actually combine these and these together. So that will be 1 over 200 plus 1 over 80 is equal to VB. Then we do know that VC is equal to negative VC over 80. And so that will be negative 1 over 80 over VC, which is equal to, that will be equal to 1.25. Then this negative 50 over 200, if we move it to the other side, will be 1.25 plus 50 over 200. And if we were to compute that, we'll end up with the value of 1.5. And then doing a similar process to the other two equations, what we'll end up having is for the second equation, for VB, it's just going to be this one, since the others don't have VB as well. So that will be 1 over 80 is equal to 1 over 80 times VB plus our VC naman for this is going to be negative VC over 80 and VC over 40. So if we just move it to one side, that will just be equal to negative 1 over 80 minus 1 over 40 times VC plus, then our VD is just gonna be this one. But if we want to, since all of our variables are all over here, so our VB is already here, our VC is also here, so we just move the VD there as well. So that will be equal to plus negative 1 over 50 times VD. And that will be equal to our constant, which is 500 times 10 raised to negative 3. And that will be 0.5. And then for the third equation, it's just 10 is equal to VC minus VD. So that's just going to be VC minus VD is equal to 10. And so we already have these values here. And what we could do is just plug it into our calculator. So we could just use the systems of equations. So when we do that, we could actually find the values for each of the variables. So that would be VA would be equal to 50 volts, which is already determined early on. And then VB will be 97.059 volts. And then VC would be equal to 15.882 volts. And VD is 5.882 volts. And so that's our answer for section A of this question. So now let's move on to the second part of the problem, and that is conducting mesh analysis. So for this, we are tasked to first redraw the circuit, clearly indicating the mesh currents and also the polarities. And so with that, given that we've already redrawn the circuit itself, what we could first do is identify our mesh currents. And with that, what we could actually do is just our put them so we do know that our meshes here is going to be this one, this one, this one, and this one. So what we could do is just give them arbitrarily their directions. So what I like to do is all of these mesh currents follow a same direction unless they have, let's say, a current source already there. So for example, for this one, what I could actually do is I'll leave that going clockwise. So that's I1. This one will be I2. And then at the top, we actually have a current source of 500 mA that's going already to the left. And so what I would do here is I'll put the direction of our mesh current going to the left as well. So it will be at this direction, and that's going to be I3. And then for our fourth mesh current, I'll actually be putting them counterclockwise, more so because as we do know, for voltage sources, the current often goes negative to positive. But you could actually make it go also the same direction as I1 and I2, which is clockwise, if you think that it would be better for you that way. We could actually also note the direction of our super mesh. So super mesh is basically when we have a current source in between two mesh currents, and that's actually this one over here. And so for that, we could actually make it follow the same direction as our I1 and I2, since that current source is in between our I1 and I2. So our super mesh will go also clockwise. And then next, what we'll have to look for is the polarities. And aside from the polarities or the direction of our mesh currents, we could also determine the polarities of our resistors. So the polarities of the resistors greatly depend on which mesh current they're in. So for 200 ohms, since the only mesh current that it is in is I1, then we can actually already know that it's going to be from positive to negative, since it is a resistor. And then for 80 ohms, it's actually in between I3 and I2. So that means the polarity would differ for I3 and I2. Uh, yeah. So for I2, by the time that it goes to 80 ohms, it's already gonna be going to the right. So what our polarity for I2 the I2 mesh current would be positive to negative here. And then for I3, actually it's also going to go to the right. So that means that for this case, the polarity would also be positive on the left and negative on the right. But actually, if let's say you put RI2 going the other direction, we'll actually end up having negative here and positive here. And it's fine that it's different for I2 and it's different for I3. Since when you do your equations, you'll end up having the correct polarity in the end. And then next, for 40 ohms, it's in between I2 and I4. So for I2, when the current reaches that resistor, it's going to be going downward. And I4 as well, it's also going to be going downward. So that means that the polarity for both mesh currents would be the same. So it's going to be positive and negative at the bottom, positive here, negative at the bottom again. And then for 50 ohms, that's just in the fourth mesh current. So when it goes there, it's gonna be going upwards. So it's gonna be positive at the bottom, negative at the top. And so yeah, that's it for the first part. Next, we have to set up the mesh equations. So similar to what we did for nodal analysis, we first determine all known values. And usually, the ones that we do know the values of are the currents in which there's a current source, and that current source is not in between any other mesh current. And so, among all of the current sources here, the only one that would fit that description is the 500 mA at the upper part of or at the I3 mesh current. So we do know now that I3 would be equal to 500 times 10 raised to negative 3 ampere. And the next, similar to what we did for nodal analysis, for unknown currents, we then make a KVL equation. So for a KVL equation, for each of the meshes, what we can do is voltage rise, the summation of all voltage rise is equal to the summation of voltage drop. So with that, let's now look into first our super mesh, which is in between 1 and 2. So since it's a super mesh, we can actually treat this as our entire mesh, our mesh our mesh current. So it's going to be like this. And then with that, we could first identify our V rise. And since the um only voltage source is this one, 50 volts, and the others are resistors, our only V rise would be the 50 volts. So if we put it here, that would be 50 is equal to V200, V200 plus V80 plus V40. So if I just write this down now, we have this equation. And then what we could actually do is, since we are actually looking for the currents, we could convert these voltages into our currents, which we could use with the equation V is equal to IR. And with that, for 200 for the 200 ohms, that will be the only current that's hitting 200 ohms is just I1. So it's going to be 200 times I1. Then for the 80 ohms, it's actually in between I3 and I2. And we do know that if I3 and I2 passes through this resistor, it's going the same direction. So we could actually add them together. So that would be I2 plus I3, which is 500 times 10 raised to negative 3. And then for V40 naman, it's gonna be, it's in between I2 and I4, which is both going the same direction downwards, and also follows the positive to negative polarity here. So that means that we could actually do is 40 times I2 plus I4. And that will actually be our first equation. And then with that, we could actually make another equation with our super mesh, and it will be using this variable, the 750 MA. So for this, in determining what are the signs of our I1 and I2 in this equation, is we actually base it on what would be the direction of the current once it passes through this current source. So for I2, when it passes through the 750 MA current source, it's actually going upward, which follows the direction stated in this circuit. However, for I2, once it goes to that, it's going downwards, which is opposite that. So it will be 750 MA is equal to I2 minus I1. So that would be 750 times 10 raised to negative 3 is equal to I2 minus I1. And that will be our second equation. And then next, for the KVL at mesh 4, so it's this one. Similar, we find the voltage rise and then equate that to the sum of all the voltage drops. And similar to what happened a while ago, our only voltage rise would be from the 10-volt voltage source, and our voltage drops will come from from 40 ohms and the 50 ohms voltages. So that will be 10 is equal to V40 plus V50. And then we could convert that all into our variables. So for 40 ohms, it will be 40 times I4 plus I2. Since, yeah, as I mentioned a while ago, they're all following the same path, which is going downwards, and it's from positive to negative. So that will be 40 times I2 plus I4 plus 50. And then for that, for the 50 ohms, the only current passing by that is I4. And it's that current is going from positive to negative. So it's just 50 times I4. And that will be our third equation. And so with that, we could actually put them all together, combine them all together so that we could determine the values of each. And so for similar to what we did for nodal, we combine all of the values or all of the I2 together, all of the I4 together, all of the I1 together for each equation. So for I1, in the first equation, the only one that is present here is just 200 I1. So that will just be 200 I1, then plus, we have here for I2 is actually gonna be 80 here and the 40 here. So that's 80 I2 plus 40 I2. So that's 80 plus 40 is just 120. So it's 120 I2 plus for our I4, it's actually just this one. This one. So it's just gonna be plus 40 I4. And then we move all the constants to one side. So since all of our variables are all here at the right, we could actually move this 500 times 10 raised to negative 3. Then don't forget the 80 here. We could actually move these both into the right-hand side, or sorry, the left-hand side. And that will just end up being 50 minus 80, 50, which is already here, minus 80 times 500 times 10 raised to negative 3. And if we were to just compute that, that will just be 10. And then next, for our second equation, which is just I2 minus I1 is equal to 750 times 10 raised to negative 3, let's just rearrange that in a way that the order is similar to what we did for the first equation. So it will become negative I1 plus I2 is equal to 750 times 10 raised to negative 3, which is 0.75. And the reason for doing so is so that once we plug in these values in the calculator, we will not be confused on which is which, since it would be pretty confusing actually if we put this here at the start, I2 minus I1, and we would end up having the wrong values. And then next, for our third equation, that will be, we don't have any I1 value here. So for I2, it's just 40. So it will be 40 I2 plus, then our I4 is going to be 40 plus 50, which is 90 I4, which is equal to 10. And so given that we already have our system of equations, we could plug this into our calculator and we'll end up having these values. So we will end up having negative 0.235A, and then for I2, that's going to be 0.515A, I3 is 0.5A, and we already determined that a while ago, and then I4 is negative 0.118A. So we have negative values here, but actually for the final answer, it's better if we put it if it's clockwise or counterclockwise. And so with that, what we could do is go back to what are our directions in when we drew our mesh current. So for I1, it's going clockwise already. However, since it's negative, we'll have to go the opposite way. So that will just be 0.235A counterclockwise. And then for I2, it's positive, so that means our initial direction is correct. So here, I2 is already in clockwise. So I2 is 0.515A clockwise. And then I3 is 0.5A. If we go back again to the to what we drew a while ago, that's already counterclockwise. So I3 is equal to 0.58 counterclockwise, and then I4 is 0.118A, and then it's negative, so we have to go the opposite direction. So now it's going this way, which is clockwise. And so our answers would be as follows. So now that we actually have these values, what we could do is recheck if what we got for nodal and mesh are the same. Because if ever that they're the same, that there's a very high chance that you actually got the correct answer. So we could actually recheck this by looking at like one of our resistors. So let's say we look into the 200 ohms resistor. and see if the V value we'll get if we use our mesh analysis, or the I value we get if we use nodal is the same. So for that, we just use the equation V is equal to IR. So that will be V200 is equal to I1 times 200 ohms. And then our V200, we already established in the first part. That's going to be VB minus VA. So if we go back here, VB minus VA, and then that's equal to I1 times 200 ohms. And then if we move all of our variables to one side, it's VB minus VA all over I1 is equal to 200 ohms. And then we just plug in all of the values that we found, and we'll end up with approximately the same value. So it won't be the exact number, since we already rounded up or rounded off some numbers. And so it's fine, basta as long as it's very near to the value. Or what you could actually do is, when you get these values, you actually end up having a fraction instead. And so just use the fraction value instead, just so that you have a more accurate answer. But yeah, so that means since we got 200 ohms, that means our solution is correct. Then next, for this third question, it's to solve the power consumed by the 80 ohms resistor. So with that, there's two equations that we need for that. And that would be V is equal to IR and P is equal to IV. So for the power, at the 80 ohms, it will be P80 is equal to I80 times V80. And then what we could do is, to make it just a bit easier for us, we could change V80 into IR. So that's going to be I80 squared times 80 ohms. So if we were to just compute that, for I80, let's just go back to the drawing that we did for B, and look at I80, which is going to be over here. So I80, based from this, is actually the sum of I3 and I2. Since it's if these currents come here, it's already gonna be pointing at the same direction to the right. So it's gonna be I80 squared. So that's gonna be I2 plus I3 squared, and then multiply that by 80 ohms. And we'll end up with a value somewhat near to 82.370. And then the unit for power is watts. So that's the answer here. And for this, you could recheck it again by converting, instead of converting our V, we could actually convert our I. So that's going to be equal to V80 over 80 times V80. And that's just going to be V80 squared over 80. And then for V80, we actually go to the drawing that we did at A. So V80 here would be VB minus VC, since positive to the negative. So VB minus VC. So that will be VB minus VC squared over 80. And then we'll end up with a similar value as well. So that does just verify our answer for this part. And then next, actually, that's it for the second section. And now we move on to the third section, which focuses on Thevenin and Norton. So we're actually given a circuit here, shown here at the right-hand side. And we are tasked to actually go through this circuit step by step, so that we end up having the Norton equivalent at the end. So what we do is, we have to first solve for VTH with respect to terminals A and B, which is over here. And then next is to solve for RTH with respect to those terminals, and then draw the Norton equivalent circuit. So first, for number one, in terms of solving for VTH, what we could actually do first is to simplify the circuit. So if we look here, just looking at it, and we could actually notice that these variables here, or actually these resistors here, could be simplified into one resistor. So based from this, we could actually do it in two steps. First is we could actually simplify or combine these three circuits, or these three resistors, sorry. And we could do this since they are connected in series. So what will end up happening is our 3K, our, and then 7K, 5K is connected in series. So since it's in series, we could just add them together. It's 3,000 plus 7,000 plus 5,000, and that's equal to 15,000 volts. And so it will end up being somewhat like this instead. So there's going to be a 15K ohms here. And then that means that since we are able to simplify it in that way, we could actually combine the 15K K ohms with the 30K ohms here as they are connected in parallel. So that would be our 15K and 30K is parallel. And so, given what we know about computing for parallel, that's just going to be 15,000 times 30,000 all over the sum of both. So that's just going to be 45,000. And when you compute that, that's going to be end up 10,000 volts. And if we were to redraw the circuit again, we'll end up with this. So with that, we can now start solving since there's no other way to simplify this problem anymore. So just to note also, the reason as to usually kasi if there's like a resistor here and then we're looking for VTH or RTH VTH, we actually have to remove it. But in this particular question, there's nothing connected here. So we actually just leave it as is. So just something to note. And then now, next we could actually solve for VTH, which we could do by solving for VOC. So for this, what I decided to do was do nodal analysis, since I think for me that would be the easier thing, given that if we were to compare the number of variables, so for mesh analysis, it would be 4, since we have 4 meshes, 1, 2, 3, 4. So we have 4 meshes. But for nodal, we have 1 here, 2, 3, 4. And then we could actually already determine like 2 of those since we have 2 voltage sources that are connected to the ground. So with that, we could go with nodal and just take note that this is our ground and identify our nodes. So it will be this one as A, this one as B, and then this one will be C, and then D. And then we can just put that as our variables VA, VB, VC, and VT. And then similar to what we did in the second part of this exam is identify our known values. So our known values will actually be VA and VC since it's connected to, for VA, it's connected to 25 volts, which is connected to the ground. And then VC is 15 volts, which is connected to the ground. So we'll just take note of it here. So that's VA is equal to 25 volts and VC is equal to 15 volts. And then now that we know that, we could now start determining the unknown variables by making KCL equations. So the KCL at VB will be as follows. So for VB, it's over here. And what I just do, and so instead of like needing to determine the signs, you could actually do it. You could determine the signs. I just assume that all of the resistors are going, like all of the resistor circuit directions are going away from VB. So with that, we could actually already determine immediately that all of it is going away. So it's all going out. So 0 is equal to um V4K, or sorry, I4K plus I10K plus I20K. And then we could convert this all into our variables of V by using V is equal to IR. And so for I4K, since the direction of the current is going out, so that means it's going to be VB minus VA all over 40K. And we already know what VA is. So that will just be VB minus VA, which is 25, all over 4K. 4K or 4,000. And then for 10K, similarly, it's also the current's going out. So it will be VB minus VC all over 10K. And we do know what VC is. So VB minus 15 volts all over 10,000. And then next is for I20K, which if we were to look here again, um, the current will be going downwards or going out. And so that will be VB minus the ground, which is just going to be 0. So VB all over 20K. So it's VB over 20,000. Which we could end up, since we only have one variable here, we only have VB. We don't really have anything else. We could actually isolate VB and compute for VB itself already. So if we were to just move it around, we'll end up having 1 over 4,000 plus 1 over 10,000 plus 1 over 20,000 times VB. And then moving all the constants to one side, so that's 25 over 4,000 plus 15 over 10,000. That will end up being 31 over 4,000 is equal to 1 over 2,500 VB. And VB will now be equal to 19.375 volts. So we have VB, and then with that, we could actually compute for VTH already. Since if we were to look back here, for us to find VTH, which is equal to VOC, it is just this whole thing. So that's VB minus this, which is VB minus the ground, or VB. So if we were to just write it down here, that will be VTH is equal to VOC is equal to VB, which is equal to 19.375 volts. So that's it for number 1 of this part. And now, we now move on to the second question, which is to solve for RTH with respect to the terminals A, B. And so for this, we actually have to look into the 3 methods that were discussed to us and first determine the method that is applicable for this. So given our circuit here, if we were to look at it, there is no dependent source naman, and it's all just independent sources. So actually, all methods are applicable, but for me, what I did for this is to do method 2. So for method 2, the first step is to create a short circuit at AB. So it will be like this. It will somewhat look like this. Like we connect it here. I'll just put it here over here now. We connect it here. And because of that, we'll end up needing to cancel this out since what usually happens is the current will go to the path with the least resistance. So it will go this way instead. So we could actually cancel out that 20K ohms. And we'll end up having, yeah, basically that's our new, I guess, new circuit. So basically just removing that 20K ohms. And with that, we could actually determine ISC. So this is ISC. And so to determine that, we can actually do mesh analysis. So for mesh analysis, we have to first determine the mesh. So this will be I1. So this is an arbitrary direction. So I1 here, and then this is I2. Hindi na siya kasha, pero yeah. And then I3 here. You could actually just follow the direction of the current source, which is going naman clockwise, and then I4 here. And then we determine our known values, which will just be I3, since it's it has a current source that is not in between any other mesh. So that will be I3 is equal to 10 times 10 raised to negative 3 amperes. And then with that, we could start doing KVL for our remaining variables. So first, we'll do KVL at mesh 1. And that will be, if we look at it back again, that will be V rise, summation of all V rise is equal to summation of all V drop. And here, the only one that's rising would be 25 volts, and all of the others will be, since the resistors, it will just be going, it will be dropping the voltage. So that will be 25 is equal to um, V 4000, which if we were to convert that into, it would to the I variables, what we'll end up having is 4,000 times, if we look, 4K ohms is in between I4 and I1. And if we were to just imagine where, what's the direction, the I1 will be going this way, and then I4 will be going the opposite way. So it's going to be I1 minus I4, since the direction has to be with respect to I1. So it's going to be I1 minus I4, and that's our first equation. And then KVL at mesh 2 is gonna be uh the only one that's gonna rise is just this 15 volts. And then no, actually for this one it's actually going to drop. Sorry, that's gonna drop as it's positive to negative. So it's going downwards. Um the that will be similar to the 10K ohms resistor. So that will just be equal to 0 is equal to 15 volts plus V 10K, and then that will just be equal to 15 plus 10,000 times the current there. So the 10K is in between I4 and I2. And for I2, it's going to be, when it reaches 10K, it's going to go this direction. But for I4, it's going the opposite direction. So it's going to be I2 minus I4. That's the second equation. And then for KVL at mesh 4, this one naman is over here at the top, and they're all resistors, so they're gonna drop. So these three will all be V drop. So it will be equal to 0 is equal to 10,000. I'll just go straight to the ano na, I times R na. I won't write the V10 already. But that's 10,000 times the current that it passes through. So it's just I4. So it's going to be 10,000 times I4 plus 4,000 here is in between I4 and I2, I4 and I1. And I4 and I1, as we already noticed a while ago, is going opposite directions. So for this time, it's going to be 4,000 times I4 minus I1, since the direction should be with respect to I4. So it's going to be 4,000 I4 minus I1 plus, and then for 10K, the other 10K, it's in between I4 and I2. So we already noticed also it's going the opposite direction. So with respect to I4, that will be I4 minus I2 times 10,000. So just writing that down. And that's our third equation. And then similar to what we did, we could actually just determine the systems of equations for this. So that will be for the first equation, it would be 4,000 I1, and then I'll be leaving an extra space here since our variables is I1, I2, and I4, just to make it a bit more uniform with the others. So it's gonna be 4,000 I1s, then we don't have any I2. So what you can actually do is just do 0 plus 0 I2, then plus our I4 here is negative 4,000, so negative 4,000 I4 is equal to 25. And then for our second equation, our I1 is 0, so 0 I1. Then plus 10,000 I2. And then it's our I4 is plus negative 10,000 I4, which is equal to, if we isolate our constants, negative 15. And then that will be, that's our second one. And then for the third equation, we do have I1 here. It's gonna be negative 4,000 I1, then plus negative 10,000 I2, and then plus, we add all of our I4s, which is 10,000 plus 4,000 plus 10,000, which is 24,000 I4, and that's equal to 0. And we have our system of equations, so we'll end up with these values if we plug it in the calculus. So I1 is equal to 29 over 4,000 ampere. I2 is equal to negative 1 over 2,000 ampere. And then I3 is equal to 1 over 1,000 ampere. And so we're not yet done since we are looking for ISC. And so with that, I'll actually just move this over here. Just bring it down now. With that, we could actually determine ISC by looking back at our equation again. And so ISC here, we'll give it a direction of going downward since it's positive to negative. And we could actually treat it similar to like a super mesh. And so we actually, to get ISC, we have to add I1 and I2. But we have to take note that once I1 reaches there, it's following the same direction of ISC, but for I2, it's going upwards, so it's at the opposite direction. So ISC is equal to I1 minus I2, which is equal to 31 over 4,000 ampere. So that's our ISC. And then now next is to find RTH. So for RTH, it's equal to the voltage at the open circuit all over ISC, the current at the short circuit. So with the values we got a while ago, so our VOC is 19.375. So 19.375. Then all over our ISC, which we just computed, which is 31 over 4,000. And that's equal to 2,500 ohms. And then next for the, so we're done now with number 2. And then next for number 3, what we have to do is draw the Norton equivalent circuit. And so we do know that the Norton equivalent circuit is, our R will be the same R, but for this one naman, Norton kasi, is gonna be, it's gonna be a current source and the resistor. So we have to get IN, which is equal to VTH over R. And that's 19.375 all over our RTH a while ago, which is 2,500, which will be 0.008 amperes. And with that, we could actually just draw it here. So it's going to be 0.008 ampere. And then the resistors in parallel. So it's going to be like this. AB. And then 2,500 ohms. And so that's our answer. So yeah, that's it for this exam. And if you have any questions, feel free to let me know. And yeah, that's it. Thank you for watching.